So, you're back, thank you. Let's do some examples of quadratic functions. So can we graph the function 3x squared minus 6x plus 5, find its vertex, find its axis of symmetry? Gosh, I hope so. So, what you actually want to do is complete the square. The completing the square technique, however, does require that whatever's multiplying x squared be a 1, and we've got a 3 here. So factor out this 3, okay, from everything involving x. So instead of 3x squared minus 6x, if I factor the 3 out from everything involving x, so the 5 can stay just a plus 5. Okay. We factored the 3 out specifically so that I would just have an x squared, but then what happens here, if I remove the 3, if I divide out that 3, I factor out that 3, what's left behind is negative 2x. So that's this line right here. Now we can complete the square. So remember, to complete the square, let's just focus on what's going on inside the parenthesis. Take this number and divide it by 2. So I get a 1. Okay. But if I were to distribute out this line right here, what you'd get, if you FOILed it all out, you'd get an x squared, you'd get a minus 2x, which was exactly the point, but you'd also get a plus 1. Sorry, that shouldn't be minus 1x, it should just be x minus 1 squared. So if I have an extra plus 1, that's what's happening here. But notice what I really have is a 3 times it because there was a 3 hanging outside here. So this is really a plus 3. So to cancel it off, because I don't want to change what's going on, I have a minus 3. I'm going to clear out my pen marks and just talk about that a little bit more. Okay, so all we did was we factored out the 3, and now we're going to complete the square. Completing the square inside this parenthesis would be, call it x squared minus 2x plus 1, but that changes the value of what's going on, and we can't just do that for free. What we've really done is we've added 3. By putting a plus 1 in here, but there's a 3 on the outside, we really added 3. But I don't want to change the values. If I add 3, I'd better also subtract 3. Okay, and the whole point of completing the square is that this parenthesis term is now something squared, x minus 1 squared. So our original function can now be written in this way. A lot of students really hate completing the square. They find it tedious and they make a lot of mistakes, and they ask, well, why on earth would I possibly want to do that? Because now we can start with our generic graphing library function x squared and apply a horizontal shift, a vertical stretch, and a horizontal and a vertical shift, and just graph this by hand. Okay. So here is our generic graph of x squared. The first thing we want to do is shift right, because they didn't write the function, of course not. Overall, we want to graph this, plus 2. Okay, so you generally want to start with where your x is and work outwards from there. So the first thing that happens is this x minus 1, and that tells me, since it's underneath the square, this is a horizontal shift right by 1 unit. Moving out, the next thing that I want to take care of is this times 3, so that's this vertical stretch. So instead of a parabola like this, it's now going to open faster. It's going to be a sharper parabola. The next thing that happens is this plus 2, and that's just a vertical shift. So we shift the whole thing up by 2, and we get this graph here. But professor, my calculator or my computer can graph it just fine. Yeah, it can, and so can you. So, you know, own it. Okay, so you can graph this by hand, and there it is. You can find some intercepts. Okay, remember that if you just let x equal 0, you'll find the y-intercept, and that's quite easy. If I let x equal 0, I'm just going to get out 5. Okay. Our vertex started here. Okay. So let me go back a slide. Okay. So the vertex of the general x squared function was at the origin, and then it got shifted right 1 unit. Then something happened with a vertical stretching, but that doesn't change anything going on here on the origin, but then it got shifted up by 2. So overall, the vertex got shifted right by 1 and up by 2. So we know our vertex is at the point 1, 2. That tells me the axis of symmetry is x equals 1. It's a vertical line, so x equals something, through the vertex, which we determined was 1, 2. So it's the vertical line, x equals 1. There's your axis of symmetry. Okay. So if you can take a quadratic function and do this completing the square, first factor out the a, then complete the square. This is called vertex form for quadratic function because it is now tremendously easy to graph. Okay, you immediately have shift either right or left, depending on whether this is a minus or a plus, vertically stretch, possibly with a reflection if a is negative, and then do a vertical shift up or down if k is plus or minus, and now you've got the graph. So this is called vertex form because you immediately get the vertex h comma k. So they didn't quite explicitly say that, but the vertex is exactly the point h comma k, okay, where h can be computed according to this and k can be computed according to that. Notice both of these involve dividing by a. And what's the one number I don't want to divide by? You don't want to divide by 0. But back in our general form of a quadratic function, remember that a is not allowed to be 0 anyway, so this is fine. Okay. So the vertex is h comma k. Remember that this is exactly h and this was exactly k. The axis of symmetry is x equals h, x equals negative b over 2a. If a is positive, the number multiplying x squared is positive, it's concave up, and the vertex is the minimum. But if a is negative, it's concave down, and then the vertex is the maximum. So just using this formula here, which just comes from completing the square, you can immediately determine where the vertex is. Is it concave up or down? The minimum maximum? What's the axis of symmetry? So let's see an example. So without drawing a graph or using a graphing calculator, find the vertex and axis of symmetry of this parabola. Is it concave up or is it concave down? Okay, so I'll pause here. Some of this is easier to do than others. So for example, I think the easiest thing to answer is it concave up or concave down? You have to do very little work for that. So don't always think that the first question is the easiest part. But I'll pause, so try to determine the vertex, determine the axis of symmetry, and then determine if it's concave up or concave down. Okay, so notice that a is -2, b is 8, c is -3. So we can just use that formula, negative b over 2a, for the x-coordinate of the vertex. And I just plug in b equals 8 and a equals -2. Notice these negatives are going to cancel each other, and we end up with just 2. So the x-coordinate of the vertex is 2. What about the y-coordinate? Well, oops, pen was backwards. If x is 2, I just need to compute the corresponding y, or f of x coordinate. So we can just plug that in. We've already computed that negative b over 2a is 2. So plug it in, and you get -2. Oh yeah, sorry, the function in question was -2x squared plus 8x minus 3, just in case you didn't have it copied down. So plug in x equals 2, and you compute y equals 5. So therefore, the vertex is at 2, 5, and since I already know the x-coordinate of the vertex, we also know the axis of symmetry. It's x equals 2. So the vertex is at 2, 5, and the axis of symmetry is x equals 2. Is this a minimum or a maximum? The vertex is either a minimum or a maximum, depending on whether the parabola is concave up, in which case it's a minimum. Okay, remember, concave up means this sort of shape, and then we'd have a minimum. Concave down means this sort of shape, and then we'd have a maximum. Which one is it in this case? Well, because a was negative, it's concave down, and we have a maximum. Okay, pardon me. So how to find the x-intercepts, we'll pause here. We'll actually make a new video. This involves some familiar computations that you've probably done before, but we'll put it into a new video just to split things up.